Hello. So for this video, we will be talking about Newton's law of cooling, another application of our first order DE. So this will be our first example for Newton's law of cooling. So we have a metal bar at a temperature of 100 Fahrenheit is placed in a room at a constant temperature of 0 Fahrenheit. Okay, so if after 20 minutes the temperature of the bar is 50 degrees Fahrenheit, find the time it will take the bar to reach a temperature of 25 Fahrenheit, and B, find the temperature of the bar after 10 minutes. Okay, so let's proceed. So basically the main concept of Newton's law of cooling is that the the ambient temperature, okay, will be the max or the minimum temperature. For example, you have a cup of coffee, uh, and then the room temperature is 27 degrees Celsius. So if the coffee cools down, the lowest temperature that the coffee will cool down to is 27 degrees Celsius. It cannot go lower than 27 because it is the ambient temperature, okay, or the temperature of the surrounding. Okay, so the ambient temperature or the temperature of the surrounding is the lowest or the highest temperature possible. In this case, the metal bar is at 100 degrees Fahrenheit, and then the room is at 0 degree Fahrenheit. So our ambient temperature here is 0 degree Fahrenheit in this case. Okay. Now the cooling of a substance exhibits exponential behavior. Again, if the object is very hot compared to the ambient temperature, the cooling rate is fast. Okay, but if the temperature of the object is near the ambient temperature, the cooling rate slows down as well. Okay, so we can apply our equation dq over dt is equals to k. Okay, but in this case, okay, we have our ambient temperature. We can call the ambient temperature k q sub 0. Okay, and then in this example, the object has a higher temperature than the ambient temperature. So object minus ambient temperature. Okay, so if the ambient temperature is higher, we can swap these two variables. Okay, so again, if the difference here is very large, the change is very large as well. But if the difference is small, the rate is also small. Okay, so this will be our working temperature, which is, if we will look at the equation, again, another, okay, another variable separable equation. So our ambient temperature in this case will be 0, okay, Fahrenheit. I suggest we will try to write the ambient temperature all throughout the solving, even though in this case the value is 0, so that we can practice, okay, the habit, okay, of including the ambient temperature in the solution. So in this case, dq over q minus 0 is equals to k dt. Okay, again, variable separable, so we can already separate this one. So our working equation will be, I will write this in the center, so ln of q minus 0. Okay, okay, and then kt plus c, then remove ln by making this the exponent of e. Okay, so cancel, q minus 0 is equals to c1 e raised to k t. Okay, again, although the ambient temperature here is 0, I am including this in the equation, so to develop the habit of including the ambient temperature in the equation. So Q is equals to 0 plus C1 e raised to k t. Right? So in the case of Newton's law of cooling, the ambient temperature will always be here in the equation. Okay? Now, looking at the given, the temperature of the bar is 100 degrees Fahrenheit at the start. Okay? Meaning, at time 0, Q is 100. Right? We can substitute this at the equation. So we will have 100 is equals to 0 plus C1 e raised to k times 0. Okay? So e raised to 0 is 1. Then we will have, okay, C1 now is equals to 100 minus 0. So as you can see, C1 will always be the difference between the maximum or the initial temperature and then the ambient temperature. Okay? Once again, I will write the ambient temperature in the equation. Q is equals to 0 plus our C1, which is 100, minus 0 e raised to k times t. Okay, we have another given in the equation, which is if after 20 minutes, the temperature of the bar is 50 degrees Fahrenheit. So from this given, we can solve for the k, okay, or the rate of change, or the rate of proportionality, sorry. So at time 20, the temperature is 50 degrees Fahrenheit. So we can substitute this at the equation. 50 is equals to 0 plus 100 minus 0 e raised to k times 20. Right? So 50 minus 0 is 50, 100 minus 0 is 100, then 50 divided by 100 is 0.5. Okay? So e raised to 20k. Again, we need k, and k is the exponent of e. So to sort k, okay, out of the equation, we will ln both sides. So ln 0.5 is equals to ln of e, so cancel, is equals to 20k. So therefore, k is equals to ln of 0.5 all over 20. Again, ln of 0.5, so this is a negative value because the temperature of our object will be decreasing over time. Okay, so the change is negative. Okay, now we have our value of k. We can include this to our equation now. So q is equals to 0 plus 100 minus 0 e raised to, okay, so 1 over 20 ln of 0.5 times t. Right. So for our questions, letter A, the time it will take the bar to reach temperature of 25 degrees Fahrenheit, and then letter B, the temperature of the bar after 10 minutes. Okay. So letter A, the time it takes, okay, for the temperature to be 25 degrees Fahrenheit, and then letter B, or I messed it up, I guess. Oh yeah, I'm right. And then temperature after 10 minutes. Letter B, the Q after 10 minutes. Okay, so we can use our equation now to solve for this question. So letter E Q is 25. 0 plus 100 minus 0 e raised to 1 over 20 ln of 0.5 t. Okay. So we need to solve for t. So 25 minus 0 is 25. 100 minus 0 is 100. So we will have 25 over 100. So this will be 0.25. Okay. Is equals to e raised to 1 over 20 ln of 0.5 times time. Now to sort t out of the equation, so ln both sides. So ln of 0.25 is equals to 1 over 20 ln of 0.5 t. Okay, so t now therefore is by simplifying. Okay, so 20 ln 0.25, okay, and then over ln of 0.5. So the given is minutes, right? So the time it will take for the object to cool down to 25 degrees Fahrenheit will be 20 ln of 0.25 over ln of 0.5 minutes. Okay, and then for letter B, so we're looking for Q after 10 minutes. So applying the equation again. Okay, so Q is equals to 0 plus 100 minus 0 e raised to 1 over 20 ln of 0.5 t. Okay, then the Q after 10 minutes, right? So Q is equals to 0 plus 100 minus 0 e raised to 1 over 20 ln of 0.5 times 10, right? So 100 e raised to, so 10 times 1 over 20, so we will have 1 half ln of 0.5. Okay, so again, this is an acceptable answer, but if the choices does not contain e or ln, we can use this one. Q is equals to 100 e raised to ln of 0.5, okay, raised to 1 half. So applying another property of ln, we're in m ln of a is equals to ln of a raised to m. Right. Then e and ln will be cancelled out, so 100 times 0.5 raised to 1 half. Okay, so this is an acceptable answer. This is an acceptable answer. Right, so that ends our video. So see you on the next video.